Hey guys, let's talk about magnetism now. The convention for the magnetic field, at least outside the magnet, it points away from the north, loops back around, and goes in the south. Now, magnetic field shape is going to change based on the shape of the magnet, but the one we talked about was a bar magnet. Now, technically speaking, according to Maxwell's equations, the magnetic field lines continue straight through the magnet from south to north and then come out the north, loop around to the south, go straight through from south to north, and continue in this closed loop pattern. It's the exact same as through a solenoid, which we'll talk about in just a bit. Now, the symbol for magnetic field is B, and the unit is the Tesla. Now, things start getting really interesting when you compare electricity and magnetism. For example, a charged particle. It's only going to feel a force due to a magnetic field if that charged particle is moving. If it's perfectly still, it feels no force. And you can find that force through what's called a vector cross product. A vector cross product is a means of essentially multiplying two vectors together, kind of, to produce a third vector. So, the magnitude of a cross product isn't too bad. In this case, the force on a charged particle moving through a magnetic field that's created from somewhere else is QV cross B. The magnitude of that force, again, every vector's got magnitude and direction, the magnitude of that force is just Q times V times B times sine theta, where theta is the angle between the velocity and the magnetic field. So get this, if I have a charged particle, and it happens to be traveling in the exact same direction as a magnetic field, then it will feel no force at all. None. If I have a charged particle and it is traveling perpendicular to a magnetic field, well, then it's going to feel the most force it possibly can. And if it's at some angle, then it still feels a force, but it's reduced based on the sine of that angle. And that's the magnitude. That's your raw value. Every vector also has a direction. You can find the direction with the right-hand rule. So for cross products, basically take your right hand, palm open, stick your fingers straight toward the first vector. In this case, it'll be the velocity of the particle. Next, you'll kind of rotate your arm until your palm is pointing in the direction of the second vector. The second vector in this case would be the magnetic field. And finally, your thumb will be the resultant vector. In this case, the resultant vector is the force. So remember what part of your hand goes to what. Sometimes I won't necessarily give you the first two and ask for the resultant. Sometimes I'll tell you the direction of the force and the direction of the velocity and ask you which way the magnetic field was pointing. So be aware of that. This vector cross products involve 3 dimensions. So it's not just going to be enough to have up, down, left, right, into the page, out of the page. That is going to be enough. It's not going to be enough to have up, down, left, right. You also need to add into the page, out of the page. That was a fantastic 30 seconds of my life. Anyway, make sure you know the symbols for out of the page and into the page. Out of the page is a little circle with a dot in it. Into the page is a circle with an X over it. Now, one important note, negatively charged particles experience the force in the exact opposite direction as positive particles, which shouldn't be a surprise. That's the case for electric forces. That's the case when you put a charged particle in the electric field, the negative goes in the opposite direction. It's also the case when electricity and magnetism are exerting forces. So, when you experience a negative particle, be it an electron or some other particle with a net negative charge, you can either just use your left hand rather than your right hand, or you could just remember to change your final answer by 180 degrees. Let's say we get a bunch of charged particles and send them all through a wire. That is called current. Remember that conventional current is the flow of positive charges, so we use the exact same right-hand rule. And I'm only going to ask you about conventional current. So if you're asked about the force on a wire, it will not involve negative particles. F equals IL cross B. The magnitude of the force, again, is ILB sine theta, where theta is the angle between which way the wire is pointing and which way the magnetic field is pointing, then you're going to use that exact same right-hand rule. The fingers will point in the direction of the current, the palm will point in the direction of the magnetic field, and the thumb will be the direction of the force that the wire feels. So these two things, F equals QV cross B and F equals IL cross B, that involves charged particles moving through a magnetic field that already exists from somewhere else. But at the same time, wires produce magnetic fields as well. So let's look at the example of a straight wire. Ooh, I should probably amend this slide. The magnitude of the magnetic field produced by a long straight wire. There we go, that's better. That magnetic field is going to be mu naught times I over 2 pi r. Long straight wires produce circular magnetic fields, and the strength gets weaker the farther away you get from the wire. Mu naught is the permeability of free space. That's 4 times pi times 10 to the negative 7 Tesla meters per ampere. And like other constants in this unit, it will be provided for you on the test. So a picture of what that right-hand rule looks like. It's the second right-hand rule, and basically since the current's going in a straight line for a long straight wire, I will take my thumb and point it in the direction of that current, keeping my palm open to begin with. Then as I begin to close my palm into a fist, my fingers start to curl, and that'll give me the beginning of the direction of that circle. So once you've got the total circle as it circles around the wire, odds are I'll ask you what direction it's going at a certain point near the wire. So, for example, if I've got a current running up to the top of the page, to the left of it, it'll be coming out of the page, and at a point to the right of it, it'll be going into the page. Back behind the wire, it'll be cutting across to the left, and in front of the wire, it'll be cutting across to the right, and circling in that pattern. Where if you tilted your view and looked at it from above, it would be going counterclockwise. And that's just one example. But that's the magnetic field produced by that wire. When a wire produces a magnetic field, it does not feel a force because of that magnetic field. Now, if you've got a current loop or a solenoid, it acts like a bar magnet. So the magnetic field, just like in a bar magnet, runs straight through it, comes out one side, that's effectively the North Pole, and loops around to the other side, that's the South Pole, then runs in a straight line through it. To figure out the direction, you'll use the third right-hand rule. Now the third right-hand rule is exactly the same as the second, except this time your current is going in a circle, and your thumb is the direction of the field in the middle of the solenoid when it is traveling in a straight line and not looping back around. So, for the second, third right-hand rule, ask yourself what is in a straight line, what is in a circle. Straight line gets the thumb, circle gets the curl of your fingers. Now the magnitude of the magnetic field inside an ideal solenoid, right at the center, is mu naught times N times I divided by L, where L is the length of the solenoid. Now, the length of the solenoid is not the total length of wire that's used to make it. Instead, it's basically just the raw distance from where the loop started to where the loop ended. So the more loops you can fit into a wire and the more tightly you can compress it, reducing the length as much as possible, the stronger magnetic field you're going to get. And this is basically what MRI machines are. If you've ever been inside one, you're put inside a little tube, and all around that tube is a coil of wire that's running around you. When you turn it on, it sends a magnetic field through you that can be used for imaging. Also, electromagnets work this way. When you turn it on, it produces a magnetic field that turns something into a temporary magnet. When you turn the current off, the magnetic field goes away, it is no longer a magnet. So like junkyards that have to lift up cars and whatnot. And then we talked about Faraday's law. Faraday's law tells me the type of voltage I can get from a changing magnetic field in a coil of wire. And that is found to be negative N times the change in magnetic flux over the change in time. So, epsilon, that's going to be the voltage that's produced. N is the number of turns of the coil that makes that up. That's the Greek letter phi, phi sub b. That's the change in magnetic flux. And this is all relative to the loop of wire. So, if the magnetic field gets stronger, or weaker in that loop of wire, you get a voltage. If the magnetic field doesn't change, but the cross-sectional area of the wire does, you get a voltage. If the magnetic field and the cross-sectional area don't change, but theta does, which is the angle relative to the field lines that the cross-sectional area has, then you get a voltage. And delta T is the time it took the magnetic flux to change. So the faster you can change this flux, the more voltage you're going to get out of it. So in summary, magnetic fields can affect wires and charged objects. If it's just a charged particle moving through a magnetic field, F equals QV cross B. If it's just a wire and it's going through a magnetic field created from somewhere else, F equals IL cross B. Both of these things use the first right-hand rule. You can also generate a voltage by a changing magnetic field through Faraday's law. That's one summary. The other is how it's basically the opposite direction, how wires or electricity can make magnetic fields. If it's a straight wire, B equals mu naught I over 2 pi r, and it's a circular magnetic field. If it's a circular wire, B equals mu naught Ni over L, and it is a straight magnetic field, at least in the middle of that solenoid. Whew, and that is all you need to know about magnetism. So that's it for video 3. Hey, how about you tune in for video 4? You've come this far. Let's go crazy.